Good morning, everyone. Can you hear me well? And so, hello again. I'm Trisha May, and I'll be your moderator this morning. So, before we start, let me remind everyone. For all attendees, turn off your microphone and webcam during the talk. Please post all your questions in the chat. This will be asked by the moderators at the end of each talk. Towards the end of the last presenter scheduled for today, the link for the evaluation form will be posted. Certificates will be awarded to attendees who attended at least 75% of all the talks in this workshop. So maybe let's just wait for the lecturer.
Okay, good morning, everyone. Magandang umaga. Okay, so hopefully my audio ako. Can you hear me?
Yes po, sir.
Okay, thank you. So good morning. Uh, so hopefully maganda yung gising natin and we have the energy to listen for today's lecture. Okay. So I think we can now start. So just to recall last time, we've discussed several aspects of numerical methods for ODEs, namely consistency. So how is your method related to, let's say, the model or the original ordinary differential equation? And we talk about also zero stability, which is concerned with stability with respect to perturbations or errors. And then the concept of convergence. Does your numerical solution converge to the true solution of your differential equation? And I've stated last time that at least for consistent single-step methods, zero stability is equivalent to, let's say, convergence. Okay. So today we will talk about a different concept of stability. Okay, and this is what we call absolute stability. And it has something to do with the limiting or the behavior of your solution as t goes to infinity. So asymptotically, what will happen to your function? Okay, you are of course interested in this case. Well, when you go to modeling, you want to know what will happen to the states of your model as time goes forward. Okay, so ano yung long time behavior nung solution ng differential equation. Okay. Now, let us consider this following very simple linear model problem. So the derivative of u, or the rate of change of u, is just basically proportional to your function. Okay. And here, let us consider a change of perspective. Let us consider the initial time to be 0, and we could say that initially it is this u naught here, u superscript 0, and it can be complex. Okay. Those who are not accustomed to complex numbers, you can just think of vectors having two components. So you can think of a point in R squared, the two in the two-dimensional plane. Okay. We very well know that the solution of this differential equation is the exponential, okay, function. Okay, so if t is equal to 0, you substitute, you indeed get this initial condition here. And if you take the derivative, you just have, you will just gain a factor lambda, and therefore you satisfy this simple model problem here. Okay, so depending on the coefficient lambda, the behavior of your solution is. What will the behavior of your solution is as t goes to infinity? Okay, and you might well know the complex exponential, okay, tends to 0, okay, as long as the real part of your coefficient lambda. Here we can also take lambda to be, let's say, to be a complex number in general, and if the real part of that is negative, then your solution tends to 0 as t approaches infinity, and the other way around. So this is a necessary and sufficient condition for the convergence of your solution to 0. And in fact, the stability is exponential. Okay, so it goes to 0 yung solution. Okay, now just to give you an idea, why do we want complex numbers? Because later, if you would like to consider systems, okay, of differential equations, let's say it is nonlinear. So first, you could probably have a linear stability analysis. So you would like to linearize your model, and in that case, this would be replaced by a linear system, where instead of a constant lambda, you have here a matrix. Okay, and as you know, for matrix, uh, for matrices, you can decompose that into a diagonal form, okay, or in a Jordan canonical form if you are familiar with linear algebra. So basically, you have the eigenvalues, and once you diagonalize that, this lambda here would be, let's say, a particular eigenvalue of your system. Okay. So here we have only considered the simple scalar case for illustration. Okay, but of course you can extend this to a linear system of differential equations. Okay, so ano ba yung ibig sabihin natin ng absolutely stable numerical method or numerical scheme? So a numerical method for this Cauchy problem here that will generate a sequence of points U sub k, where U sub k aims to approximate, let's say, the solution at the time node hk. Okay, so take note here that the initial time is 0. So the time nodes is basically what? The multiples of your step size. Okay. Now, if you let your k tend to infinity, this should also go to 0. So in other words, your numerical method is absolutely stable if it mimics this condition here that the solution tends to 0 as t goes to infinity. Okay, so as you let k to tend to infinity, your node goes to the right. To the right, and then you should also observe that it approaches a 0. Okay. Yeah. We want this for instance, if you want to model certain mechanical systems that have dissipative mechanisms in the system. For instance, yung pendulum last time, you want that some sort of physical quantities such as kinetic energy to go to 0 because it will stabilize. So as much as possible, your numerical method should duplicate that property. Okay, I'll mention here. So if we apply, let's say, the forward Euler method to this formula, okay. So basically, you replace this by uk plus 1, and then you replace this by uk, okay, and then uk plus lambda h uk. So you will gain a factor 1 plus h lambda. So again, h is the step size and lambda is the coefficient, or you can think again as the eigenvalue. And you moved this, or you can prove this by induction, that the solution provided by the forward Euler method would be 1 plus h lambda to the k u naught. Okay. Now, this is a basic a geometric sequence, right? And if we want asymptotic stability, in other words, if we want that this go to 0, what would be a sufficient condition for that one? Okay, so we want that this number should have what? A magnitude less than 1. Okay, in order for this power to go to 0 as k tends to infinity. Okay, otherwise, if this is greater than 1, then it goes to what? Greater than 0. No, if this is greater than 1, it goes to infinity. So you have instability. If this is equal to 1, then the behavior can be different. Okay, it can be oscillating in some cases. Okay, so again, if you want to guarantee that this goes to 0, this geometric sequence here, we just want this quantity to be less than 1. Okay, so this sum has magnitude less than 1, and you could check that. Well, in that case, this should be close to -1 in order for this to be less than 1. Okay. In the case of the backward Euler, so you have a minus here, and you should take the reciprocal. So if you want this to be to go to 0, you want the reciprocal of 1 minus h lambda to go to has magnitude less than 1 as well. Okay. Geometrically, that would be what? I think I have a picture here, so let's go. I think, yeah, this could be helpful. Okay, so let's go back to the forward Euler method. So if I want this to be less than 1, I need this h lambda here. So think of the product. So the product must be close to -1. More precisely, it should be the product of the eigenvalue and the step size should lie on the unit circle centered at -1, okay, with radius 1. Okay, so you could check that all numbers in this circle here would give you an absolute value less than 1 for this term here. Okay, so that is basically the unit circle, but shifted to the left. Okay. In the case of the backward Euler, you need to take the reciprocal. Okay, and you can think of this as what something close to 1. But if you want to take the reciprocal, you need to get the exterior. Okay, so in that case, if you want stability, the product of the step size in the eigenvalue should lie on the what outside of this circle. Okay, so excluding the circle with centered at 1, okay, or 1, 0 to be precise. Okay, yeah. If you go further, for example, in Hoynes method, and you can check this, you apply Hoynes method to our model, a simple model problem, and you could get this quartic polynomial in H lambda. Okay, so if you want this to be less than 1, okay, in order to have absolute stability, then you want this to you want the terms in the bracket to be less than 1, and you could recognize that this is basically the equation of the ellipse. So if you take the one with magnitude having less than 1, that would be the interior of this ellipse. Okay. And finally, for the Grant-Nicholson method, so this can be too complicated at first sight. Okay, but of course, this can be checked by a routine algebra. Okay, so you just substitute your your model to the Grant-Nicholson scheme, and you get this. Okay. Now, what if I want this to be less than 1? Okay, so if you could factor out the exponent k first. So if this product here is negative, okay, let's say this is negative, so this sum here would be less than 1 because you add a negative number. Okay, so if the product is negative, this should be greater than 1. Okay, because you add a positive number, and that has the same effect. Okay, so you have a numerator less than 1, a denominator greater than 1, so therefore the quotient would be less than 1. Okay, so if this is negative, I am guaranteed that this is less than 1. And in fact, that is also necessary. In other words, if you want this to be less than 1, then necessarily this product is also less than 1. Less than 0. I should correct myself. So this one should be less than 0. And that is illustrated in this part. So if you have a complex number with a real part less than 0, so then that should be the left plane. Okay. So as I said, those who are not familiar with complex numbers, you could just think of the Euclidean plane, okay, where the real part is the x component and the y part is the imaginary component. Okay, so with this, there's a notion of the so-called region of stability. So the region of stability is just the product of the step sizes and the eigenvalues, to which your solution tends to 0. Okay. So here we want the pair or the product h lambda in such a way that my solution would be asymptotically stable. Okay. And your method is called A stable. So A stands for absolute. Okay. Provided that this is just the left half plane. Okay. Provided that the left half plane is contained in the region of stability. Okay. So in this case, we've already discussed this a while ago. So ito yung mga region of stability ng forward Euler, Hoyne, Grant-Nicholson, and then backward Euler methods. Okay. So if you can see here, the forward Euler and the Horn methods are not asymptotically stable because what? Dapat A is stable yung method if it contains this left half plane. Okay, so, but in this case, it is not. However, the Crank-Nicolson and the backward Euler methods are A stable because it contains the left half plane. So this portion of the plane. Okay. So when it comes to, let's say, later we'll see, when it comes to efficiency, the forward Euler is efficient, but it is not absolutely stable. In the sense that, let's say, what if you have a large eigenvalue? Okay, what if this eigenvalue is large? Of course, so in order for this product to be small, you need to choose H to be small. Okay, so in other words, if you have a large eigenvalue, you need a very small step size in order to guarantee stability. Okay. So roughly speaking, for instance, your eigenvalue is located on this edge. Okay. Now, if you want to pull that eigenvalue inside, so you could multiply the eigenvalue by a small step size h. Okay. So basically, if you can recall, ano ba yung ginagawa ng what scalar multiplication, or yeah, what happens to a vector when you multiply it with scalar? Well, depending on the magnitude of your scalar, if it is greater than 1, it will it will expand. If it is less than 1, it will contract, okay, with respect to the origin. So in this case, you need a small step size in order to confine the product to lie in this case. And that is also the case of Hoyne's method. Okay, pero dito, of course, there is more room. You could probably choose a larger step size in comparison to the forward Euler. Okay. The good thing about Crank-Nicolson and backward Euler is that if you have a large negative eigenvalue, you don't need what? You don't need to rescale. Okay, you could choose a small step size, and your numerical method will be still stable. Okay, or your numerical solution will be still asymptotically stable. Kasi nandito na yung eigenvalue natin. Okay. However, these methods, take note, are very costly in comparison to the forward Euler method or the Hoyne method because you need a sub-process of root finding problem wherein you need to look for a root of a certain, let's say, nonlinear equation. For instance, you could use the Newton-Raphson method as we have discussed last time. Okay, so these are A-stable, but these are not, according to the definition. Okay, so that is stability. Yeah. So as I said, if you want your solution to be asymptotically stable with respect to the negative eigenvalues, you need to choose a small step size when you are using explicit methods. Okay, for implicit methods, you could use step sizes that are not very small. Okay, so yun yung pinagkaiba. Okay, so let's talk about the convergence of the theta method. Okay, so for technical purposes, let us assume that u is what? If you take the derivative, the second derivative and the third derivative are all continuous. Okay, and suppose that the step size, okay, satisfies this condition here. So of course it should be positive, and it is less than the reciprocal of whatever the parameter theta is, and this is has something to do with the Lipschitz constant or Lipschitz coefficient with respect to your function f dun sa ODE mo. Okay. So this is related to the Picard-Lindelof theorem last time. Let us denote the maximum absolute error of the method by E theta, okay, to emphasize that it depends on the theta. So this is a function of the step size, h. So this maximum absolute error is basically what? The largest error between the exact solution at the time node t sub k and the one given by your the approximation given by your method. Okay, it can be shown that the error consists of two parts. Okay, the first one is what the error in the initial data. Okay, and the other one is the error obtained by truncating your Taylor series in your method. Okay. So here we have several constants. I'll just mention what are these constants. So M2 is what the largest magnitude of your second derivative. M3 would be the third derivative. And C theta is just some function connected or related to the what final time, initial time, the Lipschitz coefficient, and then your parameter theta. Okay, so these are just constants. Okay, so let me mention what is the significance of this estimate here. Okay, so let us assume that the initial data is exact or precise. Okay, so this will vanish. And if you do that, you would get this order of convergence. Okay, so if you're not familiar with the big O notation, you can just think of this as some constant times h. Okay. So if theta, let's say, is not equal to 1/2, so say theta equals 0 in the case of the forward Euler method. Okay, so if this is 0, then you have 1/2 m2. So even if you make h or your step size is small, you cannot control this. Okay. Well, this will go to 0. Okay. This is constant. Okay. So the behavior of your error would be linear in this case. Okay. So, well, here we are studying the behavior as h goes to 0. Although you could see that this is a quadratic polynomial, right, in h, because you have your h squared. But as h goes to 0, because that is the way we do it in numerical methods, if you let h go to 0, the behavior of this quadratic polynomial is similar to that of a linear function. Okay, because if h goes to 0, this will vanish, this will be constant, so you end up with something like a constant times h. So if theta is not equal to 1/2, you have basically a linear order of convergence. So roughly speaking, the error behaves linearly with respect to h. So kung gaano kabilis mag-approach si h sa 0, ganun din yung error mo. Now, if you could recognize from this formula, if I choose theta to be 1/2, this constant term will be 0. So this will vanish. So in that case, you will have what? A quadratic convergence. So because here you have an h and you have another factor h here, so therefore you have a quadratic convergence in the case of when theta is equal to 1/2. And that is what? The trapezoidal or the Simpson's rule. No, not the Simpsons. The Crank-Nicolson method, I should say. Okay. So you have a quadratic convergence as h goes to 0. So with respect to a faster convergence rate, the higher the power, the larger or the faster the convergence. Okay. Because when h is small, okay, the square is smaller, right? So let's say if your step size is 0.1, the square is 0.01. So quadratic convergence is faster than linear convergence. Okay, so the higher the order, the faster the convergence is. Okay, so that's the advantage of the midpoint formula. And if you allow me, let me just go back with our diagram last time. Okay, so you could think of the error as what? Either the overestimation or the underestimation of the area under the curve. Okay, so you could see here, at least based on our intuition, that the trapezoidal rule gives me a smaller error compared to the forward Euler and the backward Euler method. Okay. So that is absolute stability and a convergence of the theta method. Okay, so going back here, so you could what in terms of efficiency, you the most efficient is the forward Euler, followed by Hoyne, and then Crank-Nicholson, then the backward. Okay, pag sinabi natin efficient, if you implement it, it will run fast. Okay, or it will run faster. However, in terms of what accuracy, okay, in terms of accuracy, the backward Euler is more accurate. Okay, so here you have what when it comes to numerical methods, you have the competing nature of or the competing uh, uh, issues of stability. No, of accuracy and efficiency. Okay. Efficiency refers to how fast the method works. Accuracy is how is the approximated or how's the approximate solution connected or how far is your approximate solution is to the exact solution. So accurate ba siya? Yeah. So in this case, you have what? An efficient algorithm, but a less accurate one. Here you have an accurate algorithm, but less efficient one. Okay. So that would be the case here. So ganon parate. If you want, let's say, if you want a very accurate what method, you need to do more things. You need to do more checking. You need to to verify more things, yeah, in order to guarantee accuracy. However, if you want efficiency, then you could tighten those conditions. You could remove certain steps, okay, in order for your method to be efficient and it will run in a faster time. Okay, so your execution time niya faster. But of course, we need to balance somewhere in between. We want we want a method that is accurate and at the same time it is efficient. Okay, so when it comes to numerical methods, in particular for ODEs, we would like to verify this some sort of convergence as here. Okay, can I observe this numerically, the linear and the quadratic order of convergence? Okay, so I'll give you one way on how to do that. You could verify the what we call the experimental orders of convergence by considering a test initial value problem. So in this lecture, I would consider this a simple problem here. So this is u prime equal to 0.5 u on the time interval 0 to 2. And the initial data is 1. So you know that we have the exact solution in this case. Again, here we have a problem with a known solution so that we could compare, okay, the numerical solution to the exact solution. Yeah. There are other ways where you could do with the absence of exact solutions. Okay. So, but I will not discuss that here. So here we have manufactured an exact solution of the problem. So the strategy is to choose step sizes, which are powers of 2, okay, or 2 raised to negative k. So we basically divide the step size into 2, okay, for 3 to 12. Okay. Hindi na tayo nag-start sa 1 because that would be a very coarse or a large step size. So, and we denote by the tilde, so u tilde hk to be the numerical solution vector. Okay, so basically your solution is a vector because you need to concatenate your approximations at each time nodes. Okay, so without a tilde, that would be the exact solution at your time nodes. Okay, now to check the order of convergence. Okay, so assuming that your numerical method has order p, so in other words, the maximum absolute error, so that's basically the infinity norm in this case. So you could just think of this as the maximum absolute error, okay, between the approximation and the exact value. So let's say it is approximately equal to a constant times h raised to p. So ito yung ibig sabihin ng method having an order p. Okay. So in the case of the forward Euler, p is equal to 1. In the case of the trapezoidal method, p is equal to 2. Okay. So here, what's the problem? I don't know the constant c in general. P is the one that we want to determine. Okay, so here we have two unknowns. Okay. So somehow we need to simplify. We need to solve C and P. Okay, but we are only interested in P. So what we could do is we could take the reciprocal of the maximum absolute errors between what hk minus 1, that's the previous step size, with respect to the current step size. Okay. Now, if you use this formula here, you just replace h by the step size hk minus 1 in the numerator and hk in the denominator. So you could cancel c. Okay, we are not interested in c, so that's good. Okay. And then here, basic laws of exponent, you could have have a common factor p here. So this is this one. Okay, so that's good. C has been eliminated. Now, if you want to solve for p, you could take the logarithm both sides. Okay, take the log. Okay, and then divide the logarithm of the ratio of the step sizes here, and then you have an approximation of p. Okay, and that is what we call the experimental or order of convergence. Okay, and take note here that it depends on your step size or the index of your step size. Okay, so this is how you would calculate the experimental order of convergence. So I think I have, you could do that here. So let me import the Python module for this SINISM, and I'll so gagamitin ko yung abbreviation na to, PYS. So this is an abbreviation for this one. Okay. Hopefully you could see. Nakita nyo? Nakita ba yung terminal?
Hindi po, sir.
Hindi. Bakit siya nawala? This one.
Okay na po.
Okay na. So I need to resume. Okay. So I've created a code just to test the errors for the single step methods. Okay. So here, okay. So let us go back. So ito yung test problem natin kanina. And this is the initial data. There's a correction here. This should be u of 0. Okay. So let's discuss this later. Yeah. Okay. So there's a bunch of numbers here. Okay. So for the forward Euler, let's see. These are the step sizes. So nag-start tayo sa 2 raised to negative 3. That is 0.25, I think, and you divide it by 2 successively. So this is by section. And you can see here the maximum absolute error. So started around 1.10 to the negative 1 until the last step size, it is around 3.3 times 10 to the negative 4. Okay, so yun yung error. This order of convergence here was obtained using this formula. Okay. So take note, we do not have an order of convergence the first step. Okay. Because you need to choose a k to be at least 1 in this case. Kasi mayroon kang k minus 1 dito. Okay. So you could see here, well, based sa theory natin, sinabi natin na yung forward Euler method converges linearly. Okay? Yan. Converges in a linear fashion. However, you could see here that the order of convergence is not equal to 1. Okay. There's some errors. Okay. Well, that is what? Reflected in our derivation a while ago, because here we have only an approximation. Okay. So that's one thing. So if you check the order of convergence experimentally or numerically, you would not get a precise order. Okay, so you would have well, a number very close to it. Okay. And of course, accounting into the fact that there are round of errors in this case. So hindi rin eksaktong 1. Okay, so if you do bisection, a linear order of convergence means the error would be also divided into 2. For instance, this one, 1.5 divided by 2 is what? Well, what's that? 7.5. So if you round off, that would be 1. Well, this is not precisely divided by 2, because take note that the order is not precisely 1. Okay, but what? Roughly, more or less, you need to divide by 2. So here you have 8, you have it, it's 4, that's 2, that's 1, that's 0.5, I think, yeah, and so on. Okay. So yun yung nature ng linear convergence. So if you divide the step size by 2, the error would be also divided by 2. And that is reflected in this graph. Okay. Hopefully you could see the graph. So in this case, I think the forward Euler is the one in green. Yeah. So this is slope. This dash line here is slope 1. Okay. So the convergence or the slope here, yeah, is equal to 1. So it follows that slope, okay, or approximately that slope. Yeah. The backward Euler has the same, has a similar order of convergence, and in fact, for our test problem, they look almost the same. Okay. For the Horn's method, it can be shown that the order of convergence is quadratic. So let's just check here. Okay, so you could see here the order of convergence is near approximately equal to 2. Ano ibig sabihin na approximately equal to 2? You divide it by 4. Okay, because that's what? 2 squared. Okay. If you divide it by 2, you divide it by 4, ganun yung error. So for instance, this one, 4, 10 to the negative 4. If you divide it by 4, the next error would be 1 to the negative 4. And if you could see also in the case of the Crank-Nicholson, you have a quadratic order of convergence. Okay. So if going back to the graph, although the Horn's method and the Crank-Nicholson's method have has the same quadratic order of convergence, ibig sabihin yung rate of decrease ay parehas, yung error dun sa Crank-Nicholson is smaller, okay, in comparison to the Horn method. Recall that the Horn method is explicit, okay, and the Crank-Nicholson is implicit. Okay, so you need to apply Newton's method, for instance, in the Crank-Nicholson scheme. So here we have an efficient algorithm, the forward Euler, let's say, but it is less accurate. Here we have what? A less efficient algorithm, the Crank-Nicholson scheme, but it is what? More accurate. Okay. So again, you need to balance between what? Between efficiency and accuracy. So probably you would like to apply Horn's method. Okay. So here, mukhang maliit naman na yung difference. Okay. And in fact, if you could make the step size smaller, then the error still goes to 0. Okay, so let me go back to the slide. Okay. Could you see the slide again?
Yes po.
Okay, thank you. Now, one might be tempted. Okay, what if I want what a small error? Okay, then what if I make my step size very small? Well, it is counterintuitive in this case. And small step size does not mean better accuracy. So if you continue the Crank-Nicholson scheme or method to our test problem, and let us just restrict the interval from 0 to 1. First, you can observe a quadratic order convergence, and then after some time, becomes stagnant. So wala nang pagbabago dun sa error. Okay? In fact, in this case, you have a slight increase. Okay? A slight increase in this case. Okay? So if you make your step size small, and if it is very small, hindi na tayo guarantee for what? For convergence. And then, in fact, if you continue this, it will stagnate. Yeah. And it will just be a horizontal line or approximately a horizontal line. Okay. So take note, for instance, even if you want to apply, let's say, or even if you want to use a built-in solver, choosing a very, very small step size does not guarantee you a better accurate result. So take note of that. Okay, how can we explain this one? So let us attempt describing that phenomena. So the case of the Crank-Nicholson scheme is based on this method. So you have the previous time node and then the average between the current and then the succeeding time node. Okay. So first we apply a centered finite difference. Okay. So here's your time node and here is your next time node. You get the midpoint. And you want to approximate the slope of the tangent line at the midpoint. What you could do is you could get the slope of the second line at the extreme endpoints. That's for the time node t sub k and tk plus 1. And that would be this quotient here. Okay. Now, if we use the one given by our ordinary differential equation, so this is basically your ODE, replacing your time with respect to the midpoint. Okay. However, we don't know the value. Okay. In fact, we are solving for u, so we don't know the value of this. So what we could do is take the average with respect to the time nodes. Okay. So you use these two approximations after multiplying by h and then adding by utk, you end up with the Crank-Nicholson scheme. Okay. So you can think of the Crank-Nicholson scheme as what? Approximating the derivative by a centered finite difference. Okay, so it's called a centered finite difference because here you use the center. Okay. And the average of your derivative using your differential equation. Okay. So you can think of the Crank-Nicholson as as a centered finite difference scheme and the average. So with that, let us concentrate on the centered finite difference method. Okay. So here, let us consider this approximation. So this is the center tau, and I have a node, let's say tau plus h on the right, and then tau minus h on the left. And this would be the difference of the time, let's say. Okay, tau plus h minus tau minus h, so that's twice the step size, let's say. However, if you evaluate this function, let's say on a machine, it is not precise. So you have some difference delta, plus minus, well, depending on the two operations that you do here. Okay. For instance, if you think of the exponential function, yung e to the x, if you plug that in the computer, let's say when x is 0 or x is 1, you will not get the precise exponential value because of course, finite digit storage. Yeah. So you have some difference, and that is denoted by delta. And you perform this in machine. Okay, so well, you could take, let's say, the symbols as calculators. So you first compute the difference, and then take what, the division, and then take the multiplication. Okay. So this is actually how you compute what, your centered finite difference. So this, based on this formula, the computed difference formula is in fact this one, which we denote with the tilde. Okay. So hindi yung exact na g, kundi yung mga computed function values na g tilde yung ginagamit. And it can be shown that the difference between the exact value and the approximated or the computed value is given by these two quantities. Okay, so let me explain ano yung ibig sabihin ng dalawang to. Okay. So delta is basically the maximum between the difference of the two function values here. Okay. Well, you can think of m1 as the largest magnitude of your function g. H is your step size. You have some order 3 times the machine epsilon. Okay. Ano yung 3 dito? Ito yung number of operations that you do. So you hear 1 subtraction, 1 division, and then 1 multiplication. Okay. Ano yung machine epsilon? So the machine epsilon is defined to be, okay, so going back to the terminal, okay, hope you could see. Kita yung terminal natin?
Yes po.
Okay, okay, so pwede. So the machine epsilon, depending on the the data type of your real number, okay. But in case of the 54-bit, I think it's 2 raised to negative 52. So it's around, it's about 2.2 times 10 to the negative 16. Okay. Ano yung definition of machine epsilon? The machine epsilon is basically the smallest number for which 1 plus the machine epsilon is still greater than 1. Is 1 plus machine epsilon greater than 1? Yes. Okay. Now, let us look at epsilon divided by 2. Okay? And then let us ask, is 1 plus the machine epsilon divided by 2 greater than 1? Okay. So, well, to have a more interactive lecture, okay, so please type in the chat box, ano yung guess nyo? Or based on your intuition, what would be the answer to this question here? Is 1 plus epsilon over 2, where epsilon over 2 has this value, greater than 1? So paki-type sa chat kung ano yung guess nyo. Or what would your intuition tells you? Don't be shy. So huwag kayong mahiya. Think of this as a survey. Okay, so dun sa Zoom, may chat doon. So, could you guess? Yes. Okay, may nagsagot na ng yes. Thank you. Ano yung iba? How about the others? Okay, my intuition tells us that it is yes. But in machine operation, this is false. Okay. Well, you should ask, is epsilon over 2, this value, is this greater than 0? Yes, that's greater than 0. But if you add that to 1, that is not greater than 1. Well, in fact, if you subtract this by 1, you get 0. And in fact, if you test, the two are equal. By the way, in programming, if you want two quantities are the same, if you want to test whether two quantities are the same, is typically denoted by this two equal symbol. Decimal reading. Uh, it's a, yes, partially, but it has something to do with what? It has something to do with machine arithmetic. Okay. So here the addition, uh, because of the storage of numbers, floating point numbers in the computer, there are instances wherein if you add a very small number to a given number, it will not change. For instance, in this case. Okay, I will not go into the details with that. You could read the what the details on floating point arithmetic, and that is more what go into the computer science part. How does the computer store numbers? Okay, in binary, and if you could see paano rin ito kinocode. But as I said, that can be what disturbing at first, but that is the reality of the machine arithmetic. So be careful. Yeah. So machine arithmetic is not the same as our what exact arithmetic. Yeah. So that machine epsilon. So going back here, back to the slides. So that is the machine epsilon provided by here. Okay. Ano yung machine epsilon na to? Yun yung kanina, yung 2 raised to negative 52 in the case of 64-bit floating points. Yan. Yung 3 dito ay yung tatlong operations involved. So in particular, you gain one machine epsilon, an error one machine epsilon for one operation. Okay. So this quantity is small, so let's ignore this at first. And let us concentrate on this one. Okay, so the first one is, let's say this is the route of error due to the inexact function evaluation. Okay. And this one is the so-called truncation error obtained by truncating your Taylor series into a second order. Okay. If you make your step size small, so this will go to 0 quadratically. However, this will explode. Okay. So for instance, what if my error in the function evaluation is at most epsilon? So you could replace this by the machine epsilon. You could find an optimal value of h. So you could minimize this one, and from calculus you could do what? You take the derivative, you equate that to 0. Okay. Once you do that, you could recognize that the optimal h is around the cube root of 3 times the machine epsilon over m3. Okay. Why do we have a cube root? So if you take a derivative here, that would be h. If you take the derivative, we'll have h squared here, and you will have a cubic equation, and you could solve that cubic equation easily. And that would be this solution here. Testing this in the exponential function, okay, what if I want to approximate the derivative at 0 using my centered finite difference scheme? So that formula would be something like this: e raised to h minus e raised to negative h divided by 2h. Okay. So if you see here, so this is slope, or this line here is the line h squared over 6. So parehas yung error natin. In fact, nag-coincide yung blue at red. So at first, the error is dominated by the truncation error. But if you make the step size very, very small, it will increase. Well, in an alternating fashion. So there's some sort of oscillatory effect in this case. Okay, and on the average, the slope follows this dashed line here, which is the slope of what? The reciprocal of the machine epsilon times h. And that is the round off errors in this case. Well, due to rounding, making the step size small does not guarantee you what? A good approximation. Ayan. So take note of that. So even if you even if you use built-in solvers, you should bear in mind that you should not choose it's very small h, because that doesn't guarantee more accuracy, and in fact it can sometimes give a poor solution. Okay, so pwedeng lumaki na yung error. And in fact, this is applicable to what? Also to the forward difference scheme. Yeah. So just a reminder, for instance, if you want to what? If you want to what? Guess, let's say, the derivative of a certain function using table of values, di ba? Yung ganun yung ginagawa natin. We use the definition of the derivative, we take h small. Okay? Be careful, because there's a certain value of h na kung saan mag-i-increase siya. Okay. Try to do that in the case of the forward method. For instance, you make this one and then you ignore the factor 2. Okay. You will not get, let's say, 1 in that case. Okay, mag-i-increase siya. So my critical value, take note of that. Okay, so I think that is enough for a single step methods. Okay. Questions before we move to the next stage, the multi-stage single step methods. Okay, so if there's none, let me discuss schematically what are multi-stage single-step methods. So here, single-step refers to, okay, we update or we get the next approximation based only on a previous one. Here, multi-stage refers to, okay, so instead of a single stage, which we've discussed so far, wherein you go directly from UK to UK plus 1, okay, you go to, let's say, temporary S stages. Okay, you could probably use the previous stage into the next stage, and then after that you use these values, okay, in order to get the next solution. Okay. So single step kasi isa lang yung difference dito. So from K to K plus 1, multi-stage kasi you go into several stages before going into the next step. So that's basically the multi-stage single-step methods. And the popular multi-stage single-step methods are the S-stage Runge-Kutta methods. And the general form is given by this. So basically, you update u sub k by a linear combination of function values with certain weights c sub r, okay, and then certain certain weights brp. Okay, so meron ka mga parameters dito, ar, cr, and then brp. Well, if you want to construct these methods for consistency, this S-stage Runge-Kutta method is consistent if and only if the sum of the weights here is equal to 1. Okay, so in other words, somehow this is what? Let's say a convex combination of the function values. Okay. So for simplicity of discussion, I will consider what we call the explicit RK methods. where most of the parameters are 0, and AR is the sum of these some sort of parameters here. So in other words, I could replace this sum by AR. Okay, so parehas yung yung coefficient dito. Okay, kung ano yung coefficient sa H, yun din yung coefficient dito sa KR sa second argument. Okay. Just to give you a brief idea how do we devise RK methods, so that we discuss the following two-stage RK methods. So the general two-stage RK method aims to solve the constant C1, C2, A2, and B21. Okay. In order for us to have a quadratic order of convergence. Okay. Well, the problem here is that how many equations do we have? We have 3 equations, right? How many unknowns? There are 4. So we are missing one equation. First, let us look at the truncation error. So the definition of the truncation error is this one. So what you do is you get the approximate derivative and then you subtract the one given by the formula. So if you transpose u sub k here to the left and divide by h, you get this sum here. That's the expression here. Okay. And then this can take some time, but well, it's not difficult to do. You apply Taylor's theorem and then apply the consistency condition. And this will supplement yung system of equations natin. Because as I said, we have 4 unknowns, C1, C2, A2, B21. Okay. Here we have 3 equations plus 1, so we have 4 equations in 4 unknowns. Okay. So after some manipulation, you could check that the truncation error is given by this expression here. Okay, so hopefully you are familiar with partial derivatives plus some second order error. Okay. You apply your ODE. Okay. Take note that U prime is equal to F. If you apply the product rule, okay, you get this total derivative here. So ang nagbago lang dito yung U double prime. If you use your ODE, you would have this one. So you apply the chain rule, I should say. So you apply the chain rule and you have this derivative here. So you have the derivative with respect to time plus the function times the derivative with respect to the second argument. Okay, so with this, if I want a quadratic order of convergence, if I'm only interested in this term, so the goal is to make this 0. And one could do that by what? Comparing the coefficients and making the coefficients the same. So for instance, I want the coefficient for the partial derivative with respect to t to be the same. So in this case, it seems that I want C2 times A2 to be 1/2. And similarly, B21 times A2 times C2, I should say, to be 1/2 as well. Okay? At kapag pinili nyo yung mga coefficients na ganon, this will be 0. Okay? And you have quadratic convergence. So here, ito yung analysis natin a while ago. And depending on how you choose the coefficients, the method that you will get. You will get the Hoyne method or the improved Euler method by choosing, let's say what? A2, B21 to be 1. So if these coefficients here are 1, then C2 would be 1/2. Okay. If C2 is 1/2, then C1 is also 1/2. And if you substitute these coefficients to our formula, cannot go back. Let's see. We substitute this here. Okay, so plug in nyo lang yung mga coefficients dyan, and you will recognize that you will end up with the Hoyne method in this case. There's also the so-called modified Euler method, wherein you choose the following parameters. So if I choose, let's say, A2, B21 to be 1/2, okay? So ano yun na yung magiging value ng C2? It would be 1. Okay? Yeah, 1. So there's a typo here. This should be 1. And then, so if C2 is 1, C1 would be 0. Okay. If you plug in, you have this formula here. Okay. So take note, the factor in C2 is what? So this is C2K2. So indeed, C2 is equal to 1 in this case. So this should be 1. Okay, so that's how you derive a two-stage RK method. So in fact, based on this, you could derive your own, or you could set up your own. For instance, you could choose C2 to be 1/4, and then in that case, B2 and B21 could be 2. Okay. If C2 is 1/4, C1 would be 3/4. And probably you could name that with another name. Okay, and still you have a quadratic order of convergence. So indeed, this is a family of an RK methods because you have here a freedom on how to choose the methods themselves. So let me comment here. The most difficult process is in fact this calculation here. Okay, so you need to be very careful on the derivatives in applying the Taylor's theorem. Nevertheless, I think it is very routine. You just need to be very careful in taking the derivatives. You could also do that, a three-stage, but I will not go into the details. To guarantee that a three-stage explicit RK method has order 3, you need these conditions. So the last condition specifically is the consistency condition. Okay? So pwede ka na mamili ng mga coefficients. So the basic RK3 is taken as follows. So paano ba? You could check, for instance, if you take these parameters, it will satisfy all of these equations here. Okay. Well, the easiest thing is this one, I think. If you sum the C's, it should be 1. So 1/4 plus 0 plus 3/4, that's 1. Okay. So I will not verify all of this. You could check. In fact, this is given in the literature, so you could check it later. There's also the RK3 Hoyne method, wherein we choose the parameters in this way. So if you check at C1, C3, and C2, if you add all of them, it is again 1. Okay. Now, by the way, there's a missing B31 here. Of course, you could solve for B31 in this formula once you know B32 and A3, which is in fact provided in this list and also in this list. Okay, so there are missing coefficients here that I've not written, but they could be derived from the equations immediately. Okay, so you do the process similarly here. Okay, so instead of the second order Taylor approximation, you do the third order Taylor approximation, and you will have a bunch of inequal expressions here. And then you need to compare the coefficients. You need to match. After matching, you will get these conditions here. Okay, so I think 15 minutes more. I think this is the very popular four-stage RK method. Ito yung pinakaalam pagdating sa Ronchi-Coulter methods. The RK4 having order 4 that utilizes the Simpson's rule. Okay. So Simpson's rule is basically the extension of your trapezoidal rule, but instead of a line, you use a quadratic approximation, a parabola, if you like. So the fourth stage, so bakit siya tinawag ulit na fourth stage? So before you update your next node, you need to evaluate, you need to do function evaluation 4 times. Okay. This is F. Okay. So you could think of this as the function value at the previous step. Think of this as a midpoint approximation, followed by another midpoint approximation, and then let's say a forward Euler approximation. So you have 4 stages in that case. So the first stage is just a function evaluation. The second and third stages, you could think of them as a midpoint approximation. And then the last stage is you can think of a forward approximation. So you use these function values, you multiply with the weights 1, 2, 2, and 1 respectively, and then you obtain this one. As you could easily verify, this method is consistent because if you add the weights, that's 1, 2, 2, and 1, divided by 6, so that's basically 1. Okay, there's a theory regarding what? RK methods. Let me just state them briefly. So if you use, so for an explicit S-stage method, the order is less than the number of stages. It's less than or equal to the number of stages. Okay. So if, let's say, if you use a 4-stage RK method, the best order that you could get is 4. However, for explicit RK methods, which I have presented, there are no methods that have order 5, 6, or 7. So when it comes to explicit RK methods, order 4 yung best na pwedeng makuha natin. Okay? If you want a higher order, then you need an explicit, no, you need an implicit method, okay? Or you need more stages. One could also verify or check the regions of stability. Okay. So dito, so this is RK3, RK4. There's also RK5 and RK6, which you could look later if you're interested. So roughly, as you increase the number of stages, the region of stability gets larger as well. However, when it comes to RK6, you can have what? A disconnected region of stability. Ano sinasabi nito? Let's say my eigenvalue is located here. If you make your step size small, then you end up with what? Somewhat a good approximation. However, if you make it smaller, it could go back to an instability. Okay, so pwede mag-change siya pagdating sa path na to. So yun lang yung different feature pagdating sa mga RK6 or particular RK6 methods. So you could have a disconnected region of stability. So again, if you increase the number of stages, you have a better or a larger region of convergence or stability, region of stability, at the expense of additional computing time, of course. Kasi kapag mas maraming stages, mas maraming function evaluations, you need more time to calculate those function values. Okay. So again, you need to balance efficiency and accuracy. So I did also I also test the RK methods that I presented, okay, kung tama ba na yung order nila ay linear, tama ba na yung order nila ay quadratic, cubic, at quartic. Okay. Yung dash lines dito, ito may slope 1, this one has slope 2, this one has slope 2, 3, and 4. So mapapansin nyo, halos parehas yung slope. Okay? However, it is not precisely 2, 3, and 4. Parang kanina dun sa Euler methods na discuss natin. And if you can notice here, okay, there's a certain step size wherein the error starts to increase when it comes to RK4. Okay? This is similar to what we have observed a while ago in the case of the Crank-Nicholson scheme. So even in RK methods, a very small step size does not guarantee you better accuracy. Again, take note of that. So those who are, let's say, using MATLAB and use ODE 45, for instance, there's a guarantee that if you use a very, very small step size, let's say 10 to the negative 4, okay, pwedeng malaki yung error or pwedeng wala nang pinag-iba kapag mamimili ka ng mas maliit na ng larger step size. Okay. In fact, we could see that here. So going back to the so let's see, it says errors for the RK methods. Okay, so take note here. In case of the RK4, if this is your step size, so hopefully you could see the highlight, this would be the error. If you divide the step size by 2, the error increases. Okay, and that is what emphasized here. If you have a negative order of convergence, in other words, your error will increase. The error increased in this case. And so from 10 to the negative 15, 10 to the negative 14. Okay, so based on this observation, again, as I said, if you want to use the RK4 method, please do not use a very, very small step size. Well, the question is, gaano kaliit? What is the optimal age? I think there's no definite answer there. It is problem specific. Okay. Yeah. So enough with the order of convergence. So for the remaining time, let me discuss, okay, a simple toy predator prey model. So let us consider the following Lotka-Volterra model. So it is a system of differential equations. Okay. So think of R as the population of rabbits and foxes for F. Okay. So the Lotka-Volterra predator prey model is a simple model that will describe the dynamics between the interaction of the rabbit population, the prey, and then the predator, which are the foxes. So let me explain this one briefly. So here, this is the growth rate of your the rabbits, and you can think of the product R and F, so the interaction between the predator and the prey, and this is the interaction rate or probability, okay, of interaction. And once the two interact, this would be the rate of predation, and it is related to the growth rate of the predators. Okay. And here we have the minus delta F. Let's say this is the natural death rate of the predators, which is in this case the foxes. Okay. So let us try to simulate this for time t 0 to 200, whatever the scale of the time is. We are not interested here at this point. We are just we just want to simulate what will happen. Okay, so let us take the following parameters. Okay, this is chosen in such a way that we have what a periodic behavior, and as you will see later. So the initial population are as follows. So 1,000 for the rabbits, and then for the foxes 30. So we apply the RKA4 method, the one that I've discussed a while ago, yeah, with what 20,000 nodes. Okay, so we need to do what time advancing 20,000 times. Okay, and that would correspond to this step size 0.01, which is basically obtained by what? Dividing this final time by the number of nodes. So I think that's correct. So that's basically 100, 1 over 100. Okay. So just to give you an idea, how is this being implemented? Let me check. By the way, if you use, let's say Python, if you want later to use Python in the future, there's a package there's a package called SciPy. It stands for Scientific Python, where you have what, where you could solve ODEs using the built-in functions, just like ODE 45, for instance. But here, the examples, all examples that I have presented so far, and I will be presenting, are custom made. In other words, I just followed the scheme, and that's implemented from scratch. Okay. So those who are what, those who like programming, you could do that as well. Yeah. So just to give you a hint or a peek on how is the code. So ang maganda sa Python, you could check the source code. Sorry. So okay. By the way, this is a custom library that I made, so that's why I'm familiar with it. So pag ginawa mo yung code, mas kabisado mo so far. So let's say explicit RK4. Okay. So here is the source code. Medyo mahaba, but let me concentrate where. Let us concentrate on this part. Okay. So basically, ito yung ginamit dun sa method. Okay. Let's see if we can recognize some of those formulas. Going back to RK4. Okay, this one. So let me just concentrate dun sa coefficients. So yung coefficients dito ay 1, 2, 2, 1, and 6. Okay. So actually, yun yung ginamit dito. Okay. That's 1, 2, 2, 1 divided by 6. And you have a factor h here, so that's an h here. Okay, so yung makita nyo mga 1/2 dito, or 0.5, that's the coefficients in this case. Okay, so basically, this line of code here is represented by these stages here. Yeah. Okay. So, in fact, yung code, kung ano yung mga formula na pinapakita ko dito, is precisely the one that is implemented. So, if we, let's say, plot the rabbit fox toy model. Okay, it takes some time. Kasi ilan ba yung... So, it's a 3x3 system. And it's 20,000. Okay. And take note, medyo matagal din because I've converted the font into the font that I'm using in the Beamer. So that's also one good thing in Python, wherein you could change the font of your labels, okay, depending on the style of your Beamer or your LaTeX. So there's a way to do that. So let me quickly discuss yung behavior dito. This is what we call a limit cycle. Okay, so this is what the population of rabbits and foxes. Rabbits versus foxes, and this is the population with respect to time. Okay. So roughly, there's a slight increase in the rabbit population or prey population, and then their population will decline due to predation. And in effect, yung red, which are the predators, will increase. Okay. However, there's some time, dahil masyado ng konti yung prey, yan, konti na yung kakainin ng mga predator, let's say, magdi-decrease yung population nila. Ayan. Until there's a critical value. Okay. Take note, this is not 0. Ayan. You could zoom that if you like. So this is not 0. Okay. So it's still above the x-axis. So there's a crucial, okay, that's all that all will almost lead to extinction, okay, of the fox. So in that case, there are now less predators. So the prey population would increase. Okay. So here, assuming that yung predator lang yung isa lang yung predator na kumakain, let's say, dun sa prey. So mag-i-increase sila. And then after some time, dahil masyado ng marami, okay, there's more food to eat, let's say, for the predators, and there's again an increase of population. And with that increase of population for the predators, the prey would again decrease. Okay, so you have this oscillatory behavior, and in fact, this is what we call a limit cycle. So we have a periodic phenomenon here. So mag-oscillate lang yung behavior in this manner. Of course, again, as I said, this is only a toy model because in reality, this is not, of course, not the case. We have neglected several or many aspects here, including, let's say, resources. We have not taken into account space, okay, kung saan gumagalaw yung predator and prey. And let's say we have not taken into account probably yung isang may major effect when it comes to environment, human, let's say, intervention. Okay, but nevertheless, we can see basic features kung ano yung ma-observe natin sa dynamics in that case. So nandun pa rin yung let's say, natural na behavior. An increase in predator population would give you a decrease in prey population. And in fact, that is reflected by this. So kapag nag-increase yung F dito, mas malaki yung pagbawas mo dun sa rate. Okay? So magdi-decrease yung population in that case. However, for a small prey, a predator, I should say, the one that you subtract here is small. Okay, so yung rate dito, well, depending on the growth rate, it either increase or decrease slowly. So you could see also in the model what you could observe numerically. Okay, so this is the one, the plot that we obtained a while ago in Python. So, so yan din yung kagandahan sa Python. If you like, if you are interested in coding, and let's say you want to adapt that in your Beamer presentations, if you're using LaTeX, you could match, okay, yung font. Okay. So you could also do customization. I think that's it for this session. So I think we will continue the discussion this afternoon on multi-step methods. So if you have questions, you could ask them right now or later. And we'll see you later this afternoon. Thank you. So kung may tanong, pwede kami magtanong. Kung wala, have a good lunch and see you later. So okay na, Trisha?
Okay na po. So kung may questions po kayo this morning, ayan, pwede nyo na pong i-drop sa chat box or sa live comment section. So kung wala, meron lang po akong few reminders. If you want to renew or apply for MSP membership, kindly scan the QR code flashed on your screen. So, flash ko lang. Yan. So the deadline for the membership is on May 15, 2021. Also, evaluation form will be posted after the talk of Dr. Peralta this afternoon. So we will resume at exactly 1 p.m. So for those who are asking kung kailan makukuha yung certificate or ID sa membership, you could email the MCS or i-message po yung Facebook account or Facebook page ng DMCS UP Public.
Okay, good afternoon, everyone. So magandang hapon. Could you hear me? Meron naman
Yes, sir.
Okay, thank you. So I think we can now start so that we could finish on time and have a rest before the plenary talk this afternoon. Okay, so before the break, we discussed multi-stage methods, specifically explicit Runge-Kutta methods. So the disadvantage or the limitation of using a single-step method is the order of convergence. So we've seen that at least in our examples, we only have a second order of convergence. And if you want to have, well, a higher order of convergence, which amounts to saying that I want the convergence rate to be faster, you need to go to a certain multi-stages. Okay, so for example, in the case of the four-stage RK method, you need to perform 4 stages amounting into 4 function evaluations. Okay, so the main disadvantage of multi-stage methods is the following. So if you want to indeed increase the order of accuracy, you need to take more function evaluations. Okay. Yeah. However, that is not necessary. And that is the aim of multi-step methods. So schematically, multi-step methods, okay, instead of using only the previous time step, we use, in this case, the previous p plus 1 time steps in order to generate the next approximation. Okay. So hindi na lang yung index k yung gagamitin natin, kundi until index k minus 1 up to k minus p. So here, in fact, you have a p plus 1 previous time nodes. Okay, so to discuss multi-step methods, and here we only focus for the linear case. So suppose that p is a non-negative integer. So a linear p plus 1 method has the following form. So first you initialize. So you have p plus 1 initial values. Okay. Here the index starts at 0 and ends with p. Therefore you have p plus 1 values here. So with this data, you advance for what indices having for k having values from p plus 1. So take note here, we have plus 1 here, from p plus 1 up to n, let's say. Okay, or n minus 1. So you advance by taking, you can think of this as a linear combination of the previous approximations plus the step size times a linear combination of the function values. Okay, at the previous time nodes plus, okay, a constant, the step size and the function value of the next time node. So here you can think of this as the function value at the time node tk plus 1. Okay. First comment, of course, here you still need to take the function values. But since these are previous nodes, you could store them, okay? And not to take the function value in that process. So you can store the function values in order not to recompute those quantities. Well, this is advantageous in the case where, for instance, you have a large system of ODEs, let's say 100 system of ODEs, which we will do later. So I will provide an example where we want to solve a system of ODEs consisting of 100 differential equations. Okay, so in that case, function evaluation would be costly and it takes some time. Okay, so in order not to repeat taking the function value, you could store them. So, saying that, that would be the disadvantage of multi-step methods. You need an additional storage for the function values. Okay. So typically, P is chosen not to be very large. Okay. And you will see later what are the specific values of P that are typically chosen. I think until 6. So in order to compensate for the additional memory that you need to take into account. So particular cases, so if P is 0, so if P is 0, you have a single step method. Okay. If the coefficient B sub negative 1 that appears here is 0, so your formula does not depend on the time node tk plus 1, so therefore the method is explicit. Well, in the case where a B is not equal to 0, this will appear, so therefore you have an implicit method. And from that, you need to, again, solve for a nonlinear equation. So you could probably, for instance, apply Newton's method as we have discussed yesterday. Okay, so the question here is that, well, in terms of the ODE, the data that I only have, let's say, is the initial data, U sub 0. Okay. How do I generate the succeeding points? So you could generate the points or the previous points using other methods. For instance, you could apply the RK4 method to generate U1 up till UP. Okay, so this is how you implement this recursive formula. So this is somewhat complicated, but if you're familiar with the Fibonacci sequence, this is somewhat similar to that, wherein you have two initial values for the Fibonacci sequence, and then to get, let's say, the next term, you need to add the two. Okay, so here, instead of just the previous values, we take the linear combination of those. Okay. So for explicit multi-step methods, we use this directly to calculate the next approximation. For implicit methods, of course, you will utilize this. You put this in some nonlinear solver, let's say, as I said, for instance, the Newton's method, and you iterate until you are satisfied with the approximation, meaning you are in a certain desired tolerance. You now choose that as your next step. Okay. So again, implicit methods take some time. Okay. However, they are more accurate as before. Okay, let me go quickly with the theory. I will not discuss in detail. So one could also discuss consistency for linear multi-step methods. So the coefficients should satisfy these two equations. So take note here, there are two coefficients. The A are the coefficients for the states or the approximations. The coefficients B corresponds to the function values. Okay. So those coefficients should satisfy these two equations. So this is somewhat similar to the RK4 method or the explicit Runge-Kutta methods that we have discussed before the break. And for additional condition, you need this one. So in devising consistent linear multi-step methods, you need to take into account this condition. Okay, so your coefficients should satisfy these two conditions. Well, a necessary and sufficient condition for a linear multi-step method to have an order Q, okay, with respect to the step size is that, okay, assuming that it is sufficiently smooth in this sense, okay, your method has order Q provided that you satisfy this, what? How many equations do we have here? Q plus 1 equations, okay? So you need to check this one. Probably you could recognize some alternating powers of J here. So the idea is basically, well, the proof is not presented here, but the idea is based on Taylor's theorem. Okay. So in particular, if you take, let's say, Q to be equal to 1, okay, or L. So therefore, L would now be equal to 1. So this will be 1 and then 1. You end up with the consistency condition. Okay. So in other words, a consistent linear multi-step method is in fact has at least order 1. Okay. How about stability? Well, the stability here is a bit more, let's say, involved. But what you do is first, okay, so let's rename the product of the step size and the eigenvalue. So this is our test problem last time. Okay. And you just put the formula on the left. So let me go back to that slide. So put all these things to the left. Okay. And from this difference equation, you will derive the so-called characteristic or stability polynomial, denoted by pi in this case. So it is the difference of rho. That's the first characteristic polynomial minus eta times the second characteristic polynomial. So basically, the first characteristic polynomial is this first difference here. So what you do, the technique is to what? Replace u by some variable, say r, okay? You make this index to be a superscript and replace k by the number of nodes. So in this case, p. So you replace this by p. So ang ginagawa lang natin dito, how would you get the characteristic polynomial of a given difference equation? Okay, so this one would correspond to rho. That's the first characteristic. And this one would correspond to the second characteristic polynomial. So they were just separated to emphasize the dependence on this parameter eta, which is the product of the step size and the eigenvalue. Okay. One could solve this, but one could look to books in recurrence formulas, let's say, and the idea is to get the roots of this polynomial, and then you generate the sum. Okay, so I will not go into the details of this, but if you solve linear systems of ODEs, okay, typically you get the eigenvalues, and then you get the linear combination of the corresponding solutions, and you have a general form of your solution. So the idea is similar to difference equations. Okay, so you would get the formula. So this is somewhat general. Okay, so with respect to, let's say, zero stability, what could check that your linear multi-step method is zero stable, provided that the following root condition holds. Okay. So you need that it is sufficient that all roots of the first characteristic, which is rho, to be in the closed unit list. Okay. Yeah. So it should have a magnitude less than or equal to 1. So all roots of your first characteristic polynomial should have roots less than or equal to 1. And if it happens that a root lies on the boundary, in other words, on the circle, then it must be simple. A simple root means that the derivative is not equal to 0. Okay, so that's zero stability. And of course, similar to single step methods, for multi-step methods, for a consistent linear multi-step method, zero stability is equivalent to convergence. Okay. So if you want to prove convergence of your method, it is enough to prove zero stability, and this is in turn equivalent to this root condition. Okay, so you just need to compute the roots of your first order characteristic polynomial. Okay, and one could do that if the polynomial, let's say, has degree 3 or more. You could use the classical root Hurwitz criterion, for instance. Yeah. Okay, there's a barrier in devising linear multi-step methods with respect to the accuracy or order of accuracy. And these are called the Darkest barrier. The first barrier states that one cannot have a zero stable Q-step method, linear multi-step method, having the order what? Q plus 1 for odd and Q plus 2 for even. Okay, so in other words, for linear multi-step methods that are zero stable, the order can be at most Q. Okay, so the order is the same as the number of steps. Okay, for odd, in the even case, the order that you can have is Q plus 1. Okay, so there are cases whether you choose an even number of nodes or an odd number of nodes. And the reason for that is related to numerical integration, but that is not the topic of this lecture, so I will not discuss that in detail. Well, next, the second barrier states that if you have an explicit linear multi-step method, then it is not stable. So later we will see linear multi-step methods for which the region of stability does not contain the left complex plane. Okay. And for linear multi-step methods, if you want asymptotic stability, your order is only one. Okay. So if you have what? An order at least 2, you will not be asymptotically stable anymore. May nag-chat. Is my audio clear?
Yes, sir.
Okay naman. So I think it's on your end. So please check your connection or your device. Okay, so let me give you an idea how to derive such methods. So let's start with the problem of what? Approximating a function with a polynomial. So we need a little bit of function approximation theory. So the polynomial interpolation problem is the following. So suppose I have a continuous function on a closed interval, and I have n plus 1 distinct nodes. Think of this as the time nodes in our problem. I want to find a polynomial having degree n, okay, that would coincide to the function values of g at the time nodes. Well, in other words, this is just polynomial curve fitting on the points on the graph, having these points that were stated here. So T1, T0, T1 until Tn. So here the degree is n, because, for instance, if you want to find a linear polynomial that will that will approximate, okay, a given curve, so least squares approximation, let's say, you need at least 2 points, right, to determine a unique line. Okay, so you need one more point with respect to the degree. Okay, so this polynomial interpolation problem is equivalent to a linear system of equations. Okay, so what you could do is, let's say I write the polynomial in this way, okay? And I want to determine the coefficients, a naught, a1 to an, okay? So how many unknowns do we have? We have n plus 1 unknowns. And again, that's why we need n plus 1 points, distinct points uh, in our sample, okay? Now, if you substitute, let's say, uh, t to be t naught in this case, so you will have uh, the first equation, which is obtained by, so I hope you're familiar with matrix vector product. So you take the inner product of this row vector by this column vector. That would be this polynomial evaluated at the time node t naught. That should be equal to g of t naught. That is given by this condition here. So you do that for every time nodes, and then you have this system here. Okay. Some of you might be familiar with this matrix. This is what we call a van der Monde matrix. And it can be shown that it is invertible. Okay, so the inverse of the matrix exists, provided that the nodes that you considered here are all distinct. Okay. So that's the reason also why we need distinct points in order for this problem to be, or for this matrix to be invertible. Okay. So you could solve this. Okay, so the more nodes, the more complicated the system is. At the van der Monde matrix suffers from round of errors. There are alternative ways in describing the interpolating polynomial by the what we call Lagrange polynomials, which you could look into the textbooks. Okay, but this is enough for illustration purposes. Okay, so polynomial curve fitting is equivalent to a linear system in linear algebra or matrix theory. Okay, yeah, so you just need to solve this. So yung red dito yung unknowns, everything here are given, provided that your function g is known. Okay. So here is an example. So for cubic for this function here, g, which is this exponential times the sine. Okay. On the closed interval 0 to 1, I will use equally spaced nodes. So let us zoom that one. So the blue curve is our function g. Here, how many nodes ginamit? Apat, 1, 2, 3, 4. So the degree would be 3. So P3 here is the cubic polynomial that will what? Pass through the nodes that are provided here. Okay, so ito yung hinahanap natin na cubic polynomial na quote-unquote mag-fit doon sa function given these data points. Okay? The more points, the better the approximation. Okay? So if I add what? In this case, yan ba dinagdag natin? We add. How many nodes do we have here? 1, 2, 3, 4, 5. So that would be a fourth degree polynomial. Okay. So this would be the quartic polynomial that would approximate your function. So you see here, you have a good approximation on this part. Okay. However, still you have a large error. Okay. Okay. So sinabi ko, the more nodes, the better the approximation. Aha. But that is not always the case. More nodes does not mean better approximation. And the classical example by Runge is given by the following rational polynomial. So here I have this 1 plus the reciprocal of 1 plus t squared on the interval -5 to 5, and we use equally spaced nodes. Okay. If you use equally spaced nodes, so here I have what, 6 nodes. So degree 5 yung polynomial at ito yung mag-fit doon. Let's add 2. So degree 7. Okay. Add 3, I should say. So you now have 8 nodes. Here you have somewhat a good approximation, but not on this part, in the latter part of the graph. Let's make the degree higher. Okay. Mukhang nagiging better yung fit dito, but it's getting worse at the latter part. If you add another degree, 2, you see, okay, better approximation on this part, but it's getting worse here. Okay. In fact, you could continue here, and the behavior is that this will either blow up or blow down. Okay. So again, that's counterintuitive. The more nodes, hopefully you should get a better approximation, but that is not the case. Well, in the situation of equally spaced nodes, at least. Okay, so be very careful in polynomial interpolation or polynomial curve fitting. Okay, if you want a better approximation, you do not need to increase the number of nodes. Okay, so be careful on that. Well, ano yung solution? Typically, what we do is we do polynomial piecewise interpolation. You do not interpolate on the whole graph as is, but you consider a piecewise polynomial. Okay? So yun yung ginagawa minsan. Okay, so having said that, a class of linear multi-step methods is the so-called Adams methods, and it's based on the following integral formulation of the ODE. So you integrate your ODE, okay, from the time node tk to tk plus 1, and you will get this equation. Then you approximate this function here by pi, okay, and what is pi? Pi here is the interpolating polynomial at the previous p plus 1 nodes. Okay, so you get the previous p plus 1 nodes, and then you interpolate. Okay, for instance, let's say this is my function, which is in blue. This is my current node. So you need to get the previous nodes, okay, and then you interpolate those data points. So in that case, that polynomial is denoted by pi here. Okay. Now, if you use equally spaced nodes, one can compute these integrals. Okay, it's a good exercise. Probably we could give that to our students, but I'll just give the formulas here. Okay, so here are the first 5 Adams Bashforth methods. So the Adams Bashforth methods are obtained by replacing this by the interpolating polynomial with respect to the time node t sub k and the previous ones. Okay. May familiar case dito. Ito. So this is basically the forward Euler method. Okay. Yeah. This is the forward Euler method. So you could calculate the coefficients, or if you do not have time to, let's say, evaluate these integrals by hand, you could just look this on textbooks, okay, or on the internet kung ano yung coefficients, okay. I think some students say if they are not interested in how the formulas are derived, and they, for instance, they only want to code it, you could just probably give the coefficients, okay. So those, for math majors, probably we could give it as a good exercise. Try it. I tried it once, but I only tried it here until p equals 2. Okay. I know the process, but sometimes, integrating polynomials, although they are easy, it can be cumbersome sometimes. Okay. So, hindi rin kailangan memorize. Ako rin hindi ko rin memorize. So, you could just look at the table of values. Yeah. I plotted here the regions of stability for the Adams, Bashforth, and Adams sa Adams Bashforth methods. Okay, so you see here that the region of stability is shrinking. Okay. However, the order of convergence is increasing in this case. We should see that later. Okay. If you compute the roots of the stability polynomial, you will get some extraneous roots. So parang itong part na to, this will not be part of the region of stability. Okay, so these are extraneous roots of the of your stability polynomial. You should only get this one. Okay, so that's the Adams-Bashforth method. We interpolate what from TK and those previous one. So since you interpolate starting from the previous node, you will have an explicit method. If you advance, let's say you add all indices up to t by 1, you get the so-called Adams-Moulton methods. So the same lang, pero in this case, you get the succeeding time node tk plus 1. So nag-move ka lang from one node to each of the corresponding time nodes here. Okay. And again, one could calculate the integrals. Of course, first you compute the polynomial, and then you compute the integrals, and then you have these formulas here. So as I said, you do not need to memorize them. You could probably look into a table, and you could just look at the values. Okay. Familiar particular cases are, so for p equals 0, you have the backward Euler method. For p equals 1, you have the Crank-Nicholson method. Okay. So yung mga na-discuss pala natin na methods last time are particular cases lang pala ng Adams linear multi-step methods. Okay. And similar to the Adams-Bashforth methods, the region of stability for the Adams-Moulton schemes are also decreasing. Okay. So the higher the number of steps, the smaller the region of stability is. However, we have a higher order convergence. Okay. And I've also tested this. Okay. By the way, I forgot to mention a while ago, para saan din ba yung order of convergence? Okay. First, this is to verify that your theory works. Ibig sabihin, tama. You just confirm your theory through a numerical example. Because you have a lot of, let's say, order of convergence, you have, and then you need to verify kung tama nga ba yung order. So that's one. Second is, you want to verify if your code is indeed true or valid. Okay. So tama ba yung code ko? So pag nagko-code ka and then you calculate the orders of convergence and it doesn't match to the one given by the theory, then one thing for sure, your code is not correct. Well, I should say that's one thing. The other thing is you should probably get a better example. Okay. Baka yung example na ginamit mo hindi mag-hold dun sa setup ng theory. Okay, so it's either your code is either correct your code or modify your code, or correct or modify your example, test example. So let us see here. So this one are the Adams-Bashforth methods. On the left and on the right are the Adams-Moulton methods. So sino yung mas accurate? These dash lines here are the same. Okay, so ano nakikita nyo, dash lines are the same. Okay, the slopes of these are 1, 2, 3, 4, and 5 respectively. Okay, similarly on the right hand side. Okay, so for order 1, parehas lang. Okay, at nakita na natin ito kanina. Halos parehas yung sa backward Euler at forward Euler, at least dun sa test example natin. Okay. But as you make the number of steps higher, the Adams-Moulton methods have what? Better accuracy. Okay, so mas mababa to dun sa line. Ito nasa taas. This one is below the line. This one is above. Okay, so AM methods provide better, accurate approximations. However, they decrease at the same rate. Okay? So parehas lang yung slope ng line. And what? Take note here, again, you have this phenomenon wherein smaller step size doesn't really give you better accuracy. Okay. So around 10 to the negative 13 yung error, I think that's a good, that's a very, very small error. So you could probably stop around this step size here. Or probably 10 to the negative 2, if you like. Okay. Again, although these are more accurate, these are, take note, implicit methods, so they take some time. Yeah. So para-parehas lang yung phenomenon na na-observe natin dun sa mga methods na din-discuss natin. Okay. Last and finally, for linear multi-step methods, if your problem is stiff, okay, loosely speaking, if you have a large condition number of the linearized system, okay, you could apply the so-called backward difference formulas. So instead of approximating the integral, okay, you use the ODE and you approximate this derivative. Okay, so you take the interpolating polynomial of the derivative at the, so how many nodes do we have here? We have p plus 2 nodes, if I'm not mistaken. Okay. Then you plug in the formulas, or else you take what? You take you look at the appropriate table on the textbooks, and you find these values here. So probably you could check what for p equals 1. Yeah. You interpolate this, and then you take the derivative. You will get this formula here. So the backward difference formula when p is 0 is nothing but the backward Euler method. Okay. So as I said, this is similar to the backward Euler method. So the region of stability is outside some island. Okay. So you have here some sort of an island of instability. So the larger the number of steps, the larger the island is. Okay. And it is somewhat similar to a limacon. Pero I think there's a flat part here. Okay. Flat part. Kung maalala nyo, pagdating sa what? Sa BDF1, that is the backward Euler method, is a circle. Okay? So that circle increases and the behavior is something like this. So BDF6, ganun din. Mas lalaki rin yung island of instability. Okay. So think of BDFs as generalization generalization of the backward Euler method, or extension of the backward Euler method. So somehow this is implemented in MATLAB. I think it's, if I'm not mistaken, ODE 23S for stiff problems. Well, I'm not sure because I cannot see the source code of the ODE 23S. So if you're interested, you could probably check that. But the idea is following these backward difference formulas. Okay. And again, you could check the order of convergence. So this is now a bit boring because they are similar before. So I'll skip this slide here. Okay. Let me see. I'm planning to have some coding. So let me discuss what briefly the so-called predictor corrector methods. Okay. Okay. I'll keep the technical details aside. Probably this is a better one. Okay. There are two types of predictor corrector methods. So one could think that these are combinations of linear multi-step methods. Wherein the first one use an explicit method and then followed by an implicit one. So here, there is what we call a PAC to the M method. So P means predict. So first, you predict the solution using an efficient, explicit linear multi-step method. Okay. And then you use that solution to correct, okay, using an implicit linear method. Okay. Because it is implicit, there's a nonlinear equation. So you need to solve this one. And one could solve that via Newton's method, or alternatively, one could apply the fixed point method. So the application of the fixed point method, or in this case, is what? You first evaluate, get the function value, and then you correct using the method. And then you repeat the process. And then you evaluate again, and then you correct. So M here represents the number of evaluation and correction steps. Kung ilang beses ka maglo-loop dito. If M is equal to 2, you need you need to perform this loop twice, and then you exit, you go to the next time step. Okay. So this is what we call the predictor corrector methods. So you predict first the solution using an explicit method. Well, we use that due to efficiency, but take note, this is less accurate. So to get a better accuracy, we need to correct the solution using an implicit method and apply a fixed point iteration. Okay, so via this process, evaluation, and then correction. There's a second version. Okay. The second version is basically, instead of going to the next step, a time step after correcting, you could probably evaluate for the last. Okay. So to cut the long story short, predictor corrector methods, roughly speaking, are just combination of the explicit methods and the implicit methods. Here we are taking the advantage of the two schemes. Explicit for better efficiency, implicit plus fixed point for better accuracy. Okay. So here we are balancing efficiency and accuracy. Ano ba yung sinasabi ng slide na to? Forget about the technical details here. Just concentrate on this highlighted part here. This limit tells us that if you, let's say, increase the number of fixed point iterations in your correction step, the stability polynomial of your predictor corrector would approach the stability polynomial of your correction step. So in this case, it would follow the stability polynomial of the implicit scheme. The main challenge in calculating the stability regions for these methods is that you don't have a closed form solutions for the formulas. For instance, here, just to give you an idea, here I applied the Adams-Bashforth 2 as the prediction, as the predictor, and then I applied the Adams-Moulton 2 for the correction. Okay. You need to solve a cubic equation. So if you're familiar with, let's say, Cardano's formula, you could probably do that, could apply that. So you need to solve a bunch of cubic equations. Okay, so dito, I think I've solved 500 cubic equations. So you cannot see the points here because there are a lot of them. So in order to to have the locus of points, you need to generate several points. So in this case, I think, if I'm not mistaken, 500 nodes yung sinolve. So just to look for the regional stability of these predictor corrector methods, one has to solve, let's say, 500 cubic equations. Of course, we don't do that by hand. We can automate that. Yeah. So, iba yung behavior pagdating sa part na to. Okay. Again, an extra evaluation would shrink this stability region. Okay. So the stability region would be the interior of these curves here. Okay, and I've also checked that indeed, based on the theory, I have what the predictor corrector methods are somewhat close to the one provided by the Adams Moulton a while ago. Okay, we want this because what? These are faster compared to the implicit methods, wherein you apply, let's say, you apply the Newton's method to solve the nonlinear system. Okay, based on this graph, I think the extra evaluation is not needed because these two are close to each other. Okay. At least for our test example. Okay, so those are, I think, all the other methods that I could discuss in this lecture. So to end the lecture, I'll give you two examples. Okay. So let us consider the following Lorentz system. Okay. So this is well known due to its chaotic behavior. Okay. And you will see later why. Yeah. Some historical background how this equation was derived. So this equation is derived from what the so-called Oberbeck-Bosenesque approximation. So this is what? How should I say this? It is some sort of a modification of the well-known Navier-Stokes equation for fluid dynamics or fluid flows, but you need to take into account the temperature. Okay. So that's what we call the Oberbeck-Bosenesque approximation. However, that is the case of that equation is the partial differential equations, a set of partial differential equations. Okay, so there's partial derivatives, but here we only have ordinary derivatives. So somehow this is an approximation of that. Well, the process was to approximate the solution by a Fourier series. Okay, you can think of sines or cosines. And then these functions here are just the amplitudes with respect to time. So if I could recall, I think x would be what? The amplitude with respect to the velocity. Y and z, I think, would correspond to the temperature. So the velocity was approximated in first order, and the second derivative, the temperature is approximated with second order. Okay. Or I should say the curl of the velocity if you want to be precise. Okay, ayan. So let us see, ano ba nangyayari dito sa system na to when, let's say, I have this initial condition. So nag-start tayo sa 1. Okay. Having these parameters. So the initial time is 0, the final time is 50. And we use 10,000 nodes. Okay, so we need to advance 10,000 times, corresponding to the step size. Well, you could calculate the step size by what? Taking the difference of the times divided by the number of nodes. Okay. What will I show you was implemented using what? The predictor corrector method that I have discussed a while ago. The Adams-Bashforth 4, so the explicit AB4 and the implicit AM4. In practice, the number of fixed point iterations is either 1 or 2. Okay. Kasi pag malaki yung M, less efficient na yung method. Okay, so ginagamit typically in practice is m equals 2. Okay, so I have those figures, so I think it's better to present them here. Could you see the terminal?
Yes, sir.
Thank you. So again, I will use the Python module for this SINISM. Okay. So let's animate the Lorentz system. Parameters. I think we have parameters here. Okay, let us run. I think, let's see. Rho is 1. Or mag-start tayo sa sigma. Okay, let's start with sigma to be 10, beta to be 2.5, and then rho to be 1. Okay, so yeah. So the initial state is 1, 1, 1. So here we plotted the x and y z components. Hindi ko nalagyan ng label, but trust me, this is x, this is y, and this is z. Okay. So ito yung initial point. So that's 1, 1, 1, I think. So that's 1, 1, and then 1 din yung x. Okay. Ano kaya mangyayari doon sa system? Saan kaya siya pupunta? Think of this as a particle. Okay. So the particle would go to? It seems that it will go to a steady state, to an equilibrium point. Okay. And so it seems that this is the steady state. Okay. What if palitan lang natin konti yung rho? Let's say what? 5? So same parameters except rho. Okay? Kung mapapansin nyo kanina, nandito yung what? Nandito yung initial data ngayon, nandito na. Okay. Now, we have a different behavior. Instead of, dun kanina, it seems that it's almost, well, somewhat linear. Here we have the convergence to a fixed point. And in fact, this is different from the earlier one. And it spirals inward, that fixed point. Okay. Increasing the parameter rho to 10. Okay, let us see. By the way, could you see the plots?
Yes, sir.
Okay. Nag-move naman?
Yes, sir.
Okay, ayan. So, tingnan natin, paano kapag nilakayan natin yung parameter na rho? Okay, so still, it spirals, but now, you can think, let's say the radius of the spiral is larger. Okay. Hindi pa tapos yung animation. Okay. And what if I say that's 20? Mukhang iba yung dynamics kasi iba yung starting point. Let's see. Okay. Mukhang mag-spiral siya dito. Gaya nung kanina. But it diverged. And it converged to another fixed point. Just changing the parameter sigma leads to a different behavior. Okay? So from 10 to 20, nag-iba. What if we increment that again by 10, let's say 30? Okay. Then what can we observe? Okay. So it seems that parehas sa kanina, but then it will go to a different part. Sometimes it stays, sometimes it will move to another orbit. So that is why sometimes tinatawag yung yung Lorentz system as the butterfly, quote unquote, the butterfly system, due to this figure here. So medyo chaotic yung behavior in this case. Hindi lang medyo. Chaotic, it's, you don't know kailan siya mag-stay dito sa orbit na to and whether it goes to another one, okay, with that particular time, okay? Lastly, let's see kung paano kayo pag 100, let's say. Okay, so probably you could see here what a piecewise line. So I think it's better to choose a smaller approximation, but let's see this case. So similar, but the difference that somehow you have some sort of a hole here. Okay. In the literature, I think this is called a twisted torus. So if you're familiar with the donut, you twist the donut and you have this behavior here. Okay. So think of an elastic donut and then you twist, you have this figure in that case. Okay. So again, this was done in using the predictor corrector method. Okay. So mabilis lang yung implementation, in fact. Okay. So you could see here, if you kapag nakita nyo nagbabago to mamaya, actually mas matagal pa yung pag-convert niya into a LaTeX file, okay, or yung LaTeX version ng code. Okay. Ayan. By the way, the classical Lorentz is given by this parameter. Okay. 10, 8 over 3, and then 28. So you could look, yan yung kinonsider ni Edward Lorentz sa kanyang paper, I think. So ito yan sa example na yan. Okay? May nag-chat chaos theory daw. Yes, that's precisely chaos theory. So if you like, you could read kung paano na-derive yung model, but basically it's obtained from a simplified fluid dynamic model. Okay. I will go back to this later. Ayan. Before I end the lecture. Okay. So balikan natin mamaya yan. Or I think we could do it now. Okay. Now, before going to the next example, if we have time, okay. Kung wala, I'll leave it probably there. May gusto bang magtanong? Questions? Before we proceed? So I think I end my example here. I'll just give another example related to the chaos theory with this one. Okay, so if you have questions, before I'll give you, okay, a sample coding. May tanong ba tayo? So far? So if there's none, So I'll give you an example on how to implement the RK4. Okay. So yung pinakita ko kanina, gumamit tayo ng predictor corrector method, but I think hindi enough yung time kung i-code ko yung method na yun. But let me go to the more simple and, as I said, more popular RK method. So let me open again the slides. Okay. Could you see these equations here?
Yes, sir.
Okay. Yan. So kasi hindi ko kabisado yan. We would code that one. So ipakita ko kung paano kinode a version of an animation of the one that I've showed you a while ago. But I will modify it as you will see. So hindi yung precise example yung ibibigay ko. So let me exit this one. Okay. Here, I will use the Vim editor for my code. Okay. I know there's a lot of editors there, IDEs that you could use in Python. I think if you install Python using the so-called Anaconda distribution, okay. Ano ba yun? Tingnan natin. Tingnan ko kung ito yung Anaconda. Okay. So we're not talking about snakes here. Yeah. I open that one. Okay, so that's the site. Anaconda.org. So hopefully hindi nyo makakalimutan. You think of Python, think of another larger snake, that's Anaconda. You could download Python here. Okay. Nasaan ba yung download niya? Here, download Anaconda. Wait. So depending on your operating system, you could install that one. So here you could probably install. So may lalabas na several editors. For example, you have here, hindi siya mabasa, but this is Spider, or you could use IPython. I think there's an IPython here. Yun yung ginagamit ko kanina, or you could use PyCharm. And so these are all editors that you could use. Maganda dahil minsan may syntax coloring and then may syntax suggestion. Okay, so ito, install niya yung mga other packages. So if you want array processing, there's NumPy. Okay. If you want scientific computing, there's SciPy. Okay, ano pa ba yung plotting? That's Matplotlib. Okay. Pandas for data science. I think scikit-learn for machine learning. Okay. So dito may mga packages na kung saan depende dun sa needs mo. Meron ng mga built-in functions na pwede mong piliin. So these are not in the standard library of Python. So these are, one might say, third-party packages. Yan. So hindi lang Python, quote-unquote, yung in-install ng Anaconda, kundi pati rin itong mga to. Okay. So if you like, you could download that and you could search for some tutorials on the internet on how to use these packages here. Ayan. Okay. So ano yung sinabi ko kanina? I will use Vim. So let's call this Lorenz.py. So that's the file extension for Python codes. Meron na ako na-create. Okay. Should I discuss? Let me just show you the code. Okay. Para hindi na tayo mag-type. Okay. Or ano yung gusto nyo? Would you like to do it from scratch? Or I'll show you the code later. What is your preference? Do we have enough time? Hanggang anong oras tayo, GB?
Until 2:30, sir.
Until 2:30. Code, then discuss. Okay. Code, ano yun? Code implies discuss? Or, okay, sige. Let's code that one. Lorentz animate, let's say. Animate Lorentz. Okay. Or Lorentz system. Okay. So let us put a comment here. Where's that? Let me save that first. So let's put a comment or a short description. Let's say animation of the Lorentz system. So this is just a brief description. Of course, if you have more time, you could put a more informative documentation of your code. So I'll just import yung matplotlib for this. So this is for plotting. Okay. So this is the package, this is the module, and this is the abbreviation. Since we are plotting in a three-dimensional scheme, I think we need. So I have a cheat sheet here. You don't need to memorize this. Okay. At first, this can be what doesn't make sense, but if you are used to it, nakabisado mo rin yung code. Or you could copy it from your previous code. So this is the library for 3D plotting. Okay. MPL toolkits.mplot3d. And for array processing, we use NumPy. Okay. And abbreviate that as NP. Okay. So let us first define the Lorentz system, or more precisely, the right-hand side. So we have here the vector u. Okay. U would be the vector x, y, z. Yeah. You have the parameters rho, beta, and then sigma. Okay. So let's say this is what? Right-hand side of the Lorentz system. Right-hand side. Okay. Well, since we have a limited time, you need to probably discuss kung ano yung mga parameters, input parameters na to dun sa function mo. Okay, but I will not do that now. There is a proper way of documenting your Python codes. Okay, but for simplicity, let us write our function in this way. Okay, so let us first unpack the components. So separate muna natin si U. By the way, the simulation that I would show to you is the following. Okay, so let us. So may tatlong column dyan because we want to animate the Lorentz system with several initial data. Okay, so instead of doing a loop, we will vectorize that one. Okay, so those who are not familiar with the so-called vectorization of codes, you could ignore what I've said. Okay, so basically these are the x, y, and z components. So by the way, Python starts with index 0, unlike in MATLAB. Okay. So gagawin natin, let us compute the derivative or assign the derivative, which is this formula here. So that's what? Sigma. Oh, kailangan ko atang bilisan mag-type. Okay, so let's see. dy is equal to x times y minus beta times y. Beta times z. And then dz to be x times y minus beta times z. Aha, may mali ata ako. The second formula should be, so interrupt me if there's a mistake in the code, okay? itong formula na to. So that's it. And then we return an array, okay, consisting of the derivatives. So dy dz. Okay. Now we go to the RK4 method. Okay, nasan ba yung RK4 natin? Okay, this one. So let us define RK4. So you need the function, initial data, initial time, final time, and the number of steps. So let's say this is the explicit RK4 method. Or Runge Kuta 4-stage method. Yeah. So first you compute the step size. So final minus initial divided by n. Okay. And then you check the dimensions. Okay. So this would be the size of your system and then the size of your initial data. Okay. So the shape, so yan yung shape nung kung ano man yung rectangular array natin. And then is what solution, or we pre-allocate the solution. You could think of a tensor or a multi-dimensional matrix having these dimensions. And then so apat na. This would be 4. And then we assign the initial value. And then we do the loop. So the last time step minus 1. Okay. K1 is equal to the function values. So I'll apply this. Okay. So for simplicity, I'll just consider, let's say, the autonomous case. So your function is independent on K. K2 would be what? H of K plus. So we are just taking this function value here, 0.5 times H times K1. Okay, K1. You do that also for K3. So we hope that walang syntax error mamaya. Yeah. 0.5 times H, but now you use K2. Okay, ito. And then there's another K4. That's plus, so H na lang. H times K3. K3. Okay, and then we update. So let's say K plus 1. Dimensions natin. Or kulang tayo. I think apat dapat. Okay, so we follow this formula here. So you apply the previous node. So 1, 2, 3, 4. Okay. Plus what would be the formula? H times K1 plus 2 times K2 plus 2 times K3 plus K4 divided by 6. Okay, so that's it. And then now you return your solution. Okay, so I don't need this anymore. Okay, so let me just go quickly. The main code. These are just preliminaries. So I don't have any time to explain this, but this is how you do it in Python, let's say. So let us define the classical Lorentz. Let's say Lorentz system is equal to, so I will use the lambda function. So lambda, and then ano ba yung Lorentz natin dito? Lorentz system. So sa function of u, rho is I think 28, sigma is 10, beta is 8/3. Okay. So yan yung classical Lorentz system natin. And then let us create array of initial data. Okay. So let us form a grid from -20 to 20, and then 21 numbers. Okay, so by yung skip natin. So need to create an array by what? Creating a mesh grid. The grid. Okay. So this is your initial data. Initial time, final time, and number of steps. Okay. So T naught, TF, and N. Let's say we start with 1. Final time is 10, let's say. And let's create 1,000 lang muna. And now let's solve the system by RK4. So U would be what? RK4. So ano ba yung mga parameters natin? So function. Okay. So ano yung function natin? The Lorentz system initial data. Ano ba yung arrangement? Yes. Initial data, initial time, final time, number of steps. Okay, so let us now create the animation. This figure. So let's create a figure first. Plot that figure. Sabihin natin ano yung size. Let's say, ano ba yung ginawa ko kanina? 8 by 8, let's say. And then let's create an axis by adding a subplot. So it's a plot 1, 1, 1. So 1 by 1, isa lang yung figure natin. And then, so this, to tell Python that this is in 3D, so we need to say that the projection is 3D. Okay, mabagal yung plot kung per time step mo, so we need to skip. So we need some index, okay? So magpa-plot lang tayo kapag yung index ay, let's say, multiple of 5. So for iteration in until the range of n, okay, let us do some scatter plot. Okay. So this is the x component, y component, and then z component. Sana tama yung index natin. So 0, 1, 2. And let's say the size. Ano lang natin? Let's say to 1.5. Okay. And then let's set the limit. Okay, I pre-calculated this. So ito lang yung limit ng axis mo. Okay. So for x, -25 to 25, that's the same with y. With z, let's say from -25 to 50. Okay. Make a tight layout of the graph. And then, let us, once you plot that, let's take a pause. This is para mabilis. And then let's clear the axis, CLA. Okay. Now, what? So if the initial iteration is 0, so meaning initially, para makita lang natin ano yung initial data, let us say, let's press enter to continue. Okay. And then finally, para makita natin yung last plot, so let us repeat the scatter plot. So you just you could copy paste that. Okay. t, and then size to be 1.5. Okay, and then let's say, para alam na natin kung tapos na, let's say, done. Okay. And then let's just show the plot. Okay. So that's the code. Okay. Let's see if it is working. So I'll open another tab. It's not working. Okay. Let's save that first. Okay. Tingnan natin kung nag-work yung Lorentz system natin. Aha, may error daw. Invalid syntax. Syntax error. Aha. So there's a missing. In here. Okay. Let's go back. Okay, mukhang may runtime warning. May mali ba tayo sa system? Let's stop this first. Mukhang may mali dun sa function. So this is the problem of what? Online, on the spot na coding. So, let's see the function kung tama ba yung nilagay natin. Let's go back to the Lorentz. So that's a sigma times y minus x, rho minus z times x minus y, x times y minus beta z. Okay, that's correct. Okay, how about the RK4? Let's see. Function value half step, full step, and then 1, 2, 2, 1. Okay, tama naman. Okay, baka kailangan natin ng decimal. Okay. Okay, check. Ano ba yung parameter? Sigma is 10, beta is 8/3. Oops, sorry. Okay. Gawin lang natin float yung mga ibang numbers. Okay. May runtime warning talaga. But it gives me this one. Haha, we don't have an initial data or we have, meron na tayong initial data kanina. Okay. Okay, continue lang natin. Aha, nag-overload. Okay, so let's see. I think there's an error in the code. So let's debug that one. Let me check. Aha, should be H. So namali yung K. K yan kanina, it should be H. Okay, hopefully that will solve it. So let's quit that one, let's repeat again. Okay, so it works now. So, nagkamali lang ng isang letra. Okay, so kanina, isang particle lang yung sinisimulate natin. Okay, ngayon dito, ilan? Ano yung dimension kanina? 21. Let's see. 21 yung initial kanina, no? 21 sa X, 21 sa Y, 21 sa Z. So you could think of this as how many nodes? I think there are 9,000, around 9,200 nodes here. Okay. So isi-simulate natin yung Lorentz system using with 9,200 initial data, okay, simultaneously. Kanina kung mapapansin nyo, isang trajectory lang. So here we would observe, hopefully, the trajectories of this number of nodes. Okay. And then, in time using 1,000 times. So, in particular, yung akin natin ay around 9.2 million unknowns. Okay? That is a small ano yung behavior? Okay, so you could see here. Kailangan natin dapat bilisan yung time pag-skip. Okay. Okay. Let me stop that the moment. Medyo mabagal kasi yung nga sabi ko, pag pinat mo per time step, medyo mabagal yung plot. So let us edit this one. So ipa-plot lang natin siya kapag, let's say, hindi ko ginamit yung IDX. If, let's say, the iteration number modulo the plot, the index to show plot is 0, okay, so meaning multiple of 5, then we just plot. Okay. So hopefully this will be faster now. Yeah. So let's see here. Let's start. Okay, medyo mas mabilis na. Konti ata. Okay, yep. So ito yung parang isang steady state. Okay. So kung makikita nyo, there is some sort of globe, some sort of attractor that is a shape of a butterfly. Ayan. Kaya nga sinasabi na butterfly. Okay. Still, nandilang sila. So parang natatrap sila. Okay. The particles based on this region here, called the attractor. And that's what a future direction in ODs or a future topic in ODs, aside from a single steady state. So tingnan nyo itong maliit na point na to. Ito ay isang steady state. There's also other concept of stability na hindi lang single point, called attractors, okay, or attracting sets or absorbing sets, okay, wherein the solution stays on that region. And there's a theory on that, okay. However, I think I need to end my talk here. So thank you for listening, and hopefully you learned something. And what else? We could share this, at least the ideas, or that meron palang nag-exist ng mga ganitong methods pagdating sa system of ODs. So with that, thank you for your time. And as my terminal says here, so the lecture is done. Thank you.
Thank you, sir, for that very informative talk. So in the audience, so do you have any questions? Okay, sige. Ako na lang, sir, magtatanong.
Nahiya ata sila. Okay, sige, good. Okay. You start.
Sir, regarding po dun sa since siguro may mga teachers dito na hindi pa marunong mag-code
Yes.
sa MATLAB or sa Python. Pwede po ba nilang gawin itong differential equations maybe sa Excel siguro?
Yes, you could do that. Of course.
Oh.
You could do the method in Excel. Yes, as a first exercise, you could do that. But later, it could be, the problem in Excel is that, paano kapag ibahin ko na yung ODE? Okay, paano pag ibahin ko na later yung initial data? Okay. So sometimes it can be tedious later if you do it several times. You could do it kapag paminsan-minsan, but if you do it several times, automation is better, I think.
Okay. So, may question po dito from Sir Philip Benjamin. Can there be a separate discussion for Python soon here in SINISM?
Well, if you like, probably we could do that next SINISM. Okay. But then you could learn from, let's say in YouTube. Maraming tutorials pagdating sa Python. It's an easy language, I think. In fact, you could teach this in high school. Medyo unstable ating connection. Okay.
Oh. So, are there any other questions? Can the audience have your
slides?
slide?
Yes. I will give later. Yeah, of course. I'll just remove the pauses para may clear lang yung document. So if you want to print, para konti lang yung papel. Yeah, I could give it later.
Okay. Wala na ba?
And the code a while ago, I will show it. I will also give yung ginawa ko kanina. I will also give that to you.
Okay po, sir. So, while waiting, if there are other, so let me post the. So please click the link provided below on the chat box for the evaluation of the lecture.
Regarding yung plenary. Yeah.
So please see your email. See, we've sent, I think, another email regarding the plenary talk at 3 p.m.
Okay. At 3 p.m. Hindi siya 2:30 or 2:45? So
2:45, sir. 2:45 pala. Sorry.
Okay. Yeah. Baka ikaw
Can we open your videos, maybe, so we can have a photo ops? Hindi na po ako mag-open kasi may mabagal pa internet dito. Okay. So, ready na po bang lahat? Okay. 1, 2, 3. Second page. 1, 2, 3. Okay. Last na po. 1, 2, 3. Thank you po for attending the tracks of our cynicism.
So thank you. See you later. So attend kayo sa dun sa plenary. Ayan.
2:45 pa, hindi pa. Sorry.